Have you got the microphone on? Great. Okay. So thank you very much for coming for the seminar. It's again being streamed, and I believe it's working. At least I can see it on my computer. So if anyone's out there watching, thank you. And please do feel free to email me questions to seminar chair, not Thomas, because you'll see it right now giving this talk. Yes, so I think we should start. And so thank you very much, Thomas. And he's going to be speaking on generalization for adaptive data analysis.
Thank you very much. Okay, so I'd like to start off by telling you a motivating story. So let's imagine you've decided to enter a machine learning contest. And the contest has some tasks such as classifying a bunch of images, whether they're happy or not so happy, some big name sponsor. Basically, there's a test set of n examples, and you're getting scored by the fraction you correctly classify. Now, unfortunately, you're an incredibly lazy programmer. So rather than downloading the training data and doing a lot of work, you just submit completely random classifiers. Now, unfortunately, this means you're only going to get about half of the examples right. But you're persistent, so you keep trying, and sometimes you get a little bit more, sometimes a little bit less. But overall, you're never really going to get that far from 50%, unless you try exponentially many times. But you have a trump card up your sleeve. So what you're going to do is you're going to look at those k-1 submissions you've sent in, and you're going to select out the ones that did better than average and discard the ones that did slightly worse than average. And you combine all of these into one submission, and that submission will just take the majority vote of all of the ones you've kept. You submit that, and hey presto, suddenly you've gotten a good score. Now, this isn't a fluke. You can actually show it's a reasonably simple exercise. This is always going to happen with high probability, as long as the number of submissions you're sending in is larger than the size of the test set they're being evaluated on. So what do I mean by overfitting? Well, the kth submission is still useless. It's still just completely random if you try it on some fresh data. So what we're seeing here is that this test set is no longer representative of what this submission will do on fresh data. So something's gone wrong here, and that's what I mean by overfitting. So how does this arise? How can this happen, such a dramatic failure? So the first k-1 submissions were random. They were fine. Nothing went wrong there. It's that last one that where things went wrong. And in particular, it depends on the scores of the previous submissions. And those scores depended on the test set. So now you have a submission which depends on the data on which it's being tested. That's what's going on. So basically, there's this idea of data analysis that we get taught, where you first come up with a hypothesis, then you collect the data, and then you test it. Unfortunately, what happens in the real world sometimes is that this doesn't work, so you go back, you revise your hypothesis, and again, you're lazy, you don't go out and collect new data every time, you just reuse the same data that you collected. Data is not that easy to come by. So what's happened here is that somehow, in this example, we were in the adaptive model rather than the standard model because of this dependence that we were using. So basically, most of the work in ensuring statistical validity, ensuring generalization, preventing overfitting, lives in this model. This is the safe model, whereas this model it's really not well explored, and basically we're told to avoid this. In kindergarten, you get told, don't take candy from strangers, and don't revise your hypotheses. So what I'm going to be talking about today is what can we do in this model. This is a question that was recently studied by these two papers here. One of the authors is in the audience. Okay, so now the story that I told you was obviously cooked up. This is not a very real story, but adaptivity is a very real problem, and people have been attributing a lot of failures in science to this issue. And there's also an example of this happening in machine learning competitions, as I was saying. So there's this example where people were submitting lots and lots of submissions to the machine learning contest and using that to tweak the parameters of their algorithm. They weren't doing something as stupid as I was doing, but it was still using this idea of adaptivity to overfit. Okay, great. So I'm going to be talking today about data, people who like data, and how they interact with that. So the purpose of what I'm going to be talking about is understanding the role that adaptivity plays in terms of generalization or overfitting or statistical validity. These are basically the same term to me. And to do that, I'm going to introduce a formal model in which to study the adaptive data analysis problem. And then we can use that model to actually prove theorems and provide tools that guarantee generalization. And this is going to deepen connection with information theory and differential privacy. I'm also going to talk about impossibility results, showing that there is an exponential separation between what you can do with adaptive data analysis and what you can do with non-adaptive data analysis. That's the overview of today's talk. Okay, so this is the question you want to answer. And to answer that, we have to specify a model, and this is the model that was specified in these papers. So the key characters in the model are, first of all, a population. This is what we're interested in, what we're trying to study. And we're going to model that as a probability distribution on some space, which we'll just think of as being a d-dimensional space of d bits. And then you have someone who's interested in that population who we'll call the analyst. And an analyst has questions like, what is the score of my submission? Now, they want to know what the fraction of fresh data that their submission will correctly classify. They could also ask for a different question, like a phone polling question about political support, or maybe a more relevant question here is about Brexit. So it seems these problems are difficult to estimate. And you could also have a very complex query, like you want to fit a model to the population. But we're going to stick to a simple set of statistical queries for today's talk. And basically, a query is specified by a predicate, and the question is, what fraction of the population satisfies that predicate? Now, unfortunately, the analyst doesn't have access to the whole population, so the analyst goes and collects a sample from that population. And then that sample gets fed into some mechanism. This could be Excel or Stata or R or something else. And we're going to be constructing this mechanism. And then the analyst is going to specify his query to that mechanism. And then he receives an answer and he specifies a second query. Now, the key thing here that's adaptive is that the first answer is returned before the second query is specified. So the second query can depend on the first answer. And this continues until the kth query can depend on all the previous answers. That's where adaptivity comes in and makes things interesting. So what we want in terms of accuracy is that each answer is close to the true fraction of the population satisfying that predicate. And we'll have some accuracy parameter alpha. So what do I mean by generalization? Well, it would be easy for the mechanism to output this quantity, which we call the empirical answer. It's easy for the mechanism to say what fraction of the sample satisfies this predicate because the mechanism has the sample. But what we want is this quantity. We want to know something that's close to the true fraction of the population satisfying the predicate. This is hard because the mechanism doesn't have the whole population. And the difference between these two answers is what we're going to call the generalization error. That's the thing that's problematic. Any questions about the model at this stage?
Where is the mechanism coming in?
So the mechanism can choose how to answer these queries. It's not forced to answer them in any specific way. We're going to look at what potential strategies the mechanism could use to answer queries. Thanks for clarifying. Okay, so let's compare to the non-adaptive model. So in the non-adaptive model, all of the k queries are specified at once and all the answers come at once. Now this is the setting that we're more familiar with, and we can very easily show using a concentration inequality combined with a union bound that you can use empirical answers. So if the mechanism just outputs the empirical answers, that's kind of the obvious thing to do. Then as long as you have this many samples, you're going to get some good accuracy. And basically this is because we can sort of show that the generalization error is small with high probability by these concentration inequalities. But this argument doesn't work in the adaptive setting. And that's because you can't just take a union bound over the queries that were asked. You have to take a union bound over all the queries that could have been asked, effectively. Okay, so I've specified the model. Now we can state the formal question. How many samples do I need to collect in order to have a mechanism that's able to answer k adaptive queries to a given accuracy alpha? Now, for those of you who have a machine learning background, you could formulate this in terms of asking, if I want to simulate algorithm from the statistical query model and the PAC model, how many samples do I need to collect? That's an equivalent formulation of the question in the language of learning theory. So I've already mentioned that if you use empirical answers, if the mechanism uses empirical answers, then it's going to need a linear number of samples. So the number of samples has to be linear in the required in the number of queries. But in the non-adaptive setting, logarithmically many samples suffices. So for empirical answers, we're already seeing there's a big difference between the adaptive and non-adaptive setting. We're not, yes?
Thomas, in the learning theory literature, was there no discussion about activity?
I don't know if people were worried about polynomial factors. Going from k to the square root k, I don't know if that was ever seen as a big issue. I mean, it's a natural question, but I don't
But they were worried about sample sizes.
Right, but I think you can do a non-black box simulation, right?
True.
And many settings probably that's just the easier thing to do. What was I saying?
Sorry.
Right, so what I wanted to say is that we're not restricted to using empirical answers. We could use a mechanism that does something else. It could do something other than returning just the empirical answers, even though that's the obvious thing to do. Okay, so what's the answer to this question? So I'm just going to hide the accuracy parameter. So if we're optimistic, we could hope that we could do something clever and do the same as we did in the non-adaptive setting. Just get away with logarithmically many samples. That'll be great. We could also be pessimistic and assume that empirical answers are kind of the best thing to do. And another way to do this would, of course, be to split up your data. So you could take the data you have, split it into k subsets, and use one subset for each adaptive query you get. And that's I think, a sort of semi-reasonable approach in many settings.
Can I ask a question?
Yes.
So I suppose from a statistical point of view, you seem to be going straight to sort of rate of conversions, but I'm just wondering, before, does one have what I think of as sort of consistent estimation? And in your first sort of toy example, you were saying that by having this kind of adaptive procedure, we were going to get, however long we continue that process, we were going to get not an accurate answer. So I'm assuming that one has to have some conditions on the mechanism, even to have sort of n infinity equals infinity getting an accurate answer to a given level of accuracy. Sorry if this is a stupid question, but
right. So I mean, we do need to do some work to make sure we have a mechanism that does something reasonable. I mean, I'll tell you later what the mechanism that the mechanisms that we use are. But I mean, yeah, you're right. There is plenty of choices for mechanisms. Some of them are probably not reasonable.
But for some of them, the sample size n can increase to infinity, and you still won't achieve accuracy.
Yes, you could come up with examples.
Okay.
Okay, so that's the optimistic and the pessimistic thing, but we could also imagine that somewhere in between. So what do you think the answer is? I mean, I'm sure you can all guess that it's the interesting one of the three, so you're correct. It turns out that, and this was surprising to me, that it's necessary and sufficient to have about square root k samples to answer k adaptive statistical queries. And that's not something I sort of expected. It seems sort of unnatural. It seemed like it would be natural that one of these two estimates would be the right one. Okay, so it's also worth pointing out at this stage that this is an exponential separation between what you can do in the adaptive and non-adaptive settings. So in the non-adaptive setting, you only need logarithmic sample complexity. That means given n samples, you can answer exponentially, about 2 to the n queries, whereas here you're only going to get, given n samples, you get n squared queries that you can answer. And that's a huge difference in power. And this is inherent because this isn't just specific to one mechanism. There's really nothing you can do about this. So that I find interesting. Okay, so let me be more precise about what the results are. So for the upper bound, the theorem is that there exists an efficient mechanism, and I'll tell you what this is later, that answers k adaptive queries about an unknown distribution, and all it knows about the distribution is n samples from it. And the sample complexity is about square root k of alpha squared. Now you'll note that I have two references for this result. So the earlier reference had a slightly weaker bound, and the later reference improved that and also had a simpler proof, at least in my opinion. Now for the lower bound, what we can show, and it's almost matching, is that any mechanism that answers k adaptive queries about a distribution that doesn't know nothing about, even though apart from n samples from that, requires sample complexity square root k of alpha. Now, again, there's two references, and the earlier one had a worse dependence on k. So this one tightens it up to square root. Now, there is a caveat to this result. So you have to make one of two assumptions. Either you have to assume that the data is high dimensional. So basically the number of bits per sample is linear in the number of queries. That's a very high dimensional data. Or you have to make a computational assumption. You have to assume that M is efficient. Now, this result does have an efficient M. Now you may be wondering, is this caveat a necessary caveat? And the answer is yes. So we can actually, if we satisfy neither of these assumptions, we can do better. So there exists an exponential time mechanism. That's very inefficient. That answers k queries with the following sample complexity. So rather than having a square root k dependence, so rather than depending on the number of queries, you depend on the dimension. And you only have a logarithmic dependence on the number of queries. So in terms of the dependence on the number of queries, we're back to the non-adaptive setting. But this only is good if you have lower dimension. So it's essentially matching upper and lower bounds because we can get square root k efficiently, and inefficiently we can, if we have low dimension, we can do better. However, you'll notice that there's a gap between the lower bound, which has a 1 of alpha dependence, and the upper bound, which has a 1 of alpha squared, or in this case, 1 of alpha cubed dependence. Okay, so back to the overview. I've shown you a model for adaptive data analysis, and I've told you that empirical answers, they're great for non-adaptive queries, but they don't really work so well when you move to the adaptive setting. But we have matching upper and lower bounds for the adaptive setting, which shows that we can do better than empirical answers for adaptive queries. Now that, to me, was surprising. And it's also an exponential separation between the adaptive and non-adaptive settings. So we're seeing a really strong separation in power. But as I mentioned, the upper and lower bounds are not quite matching. There's still a gap in the dependence on the accuracy parameter alpha, which corresponds to convergence rate, and also some logarithmic factors that are hiding under these tildes that I'm not mentioning. So for the rest of this talk, I want to give you some idea of the flavor of the techniques behind these results. In particular, I want to sort of talk about the connection between these results and information theory or differential privacy. And I also want to give you some kind of idea of where square root k comes from, because that is, to me, something that is rather mysterious. Any questions at this stage? Okay, so let's talk about the upper bounds first. So this is the upper bound for the efficient mechanism. This is nice and simple. And then we have the upper bound for the inefficient mechanism, which is a bit more complicated. Now, both of these basically boil down to the same underlying concept that I'll get to later. But for now, I'll just focus on the simpler result. And I'll tell you exactly what the mechanism is that satisfies this. All the mechanism does is it computes the empirical answer and adds some Gaussian noise to that. And that's the answer it outputs. So all it's doing is outputting noisy answers. Very simple. But at this point, you're probably wondering, why would you do that? I mean, it's perfectly nice data, and you just added noise to it. Why would you want to do that? So the intuition for why adding noise is a good thing is that basically it's hard to overfit noisy data. And in particular, you're going to prevent the analyst from overfitting the data because the analyst can't learn too much about the sample you've collected. And that prevents the analyst from overfitting, it ensures generalization. Okay, so I want to make this intuition a little bit more formal by formally defining a property that is achieved by this noise addition. And the property is stability. Now, stability basically means that if you have a small change in the input, you have a small change in the output. Now, this occurs in many places, but we're going to talk about a very specific type of stability here. So what do I mean by a small change in the input? I mean, if you change your sample by 1 point, so you just take one of those n sample points and change it, that's going to be a small change in the input. And we'll look at the corresponding change in the output. Now, doing this change can only change an empirical answer by 1 over n. So that's a form of stability, but that's not the form of stability I'm going to be using. I'm going to be looking at this mechanism that adds noise, and I want to look at the distribution of that output, of that output. So in particular, what we have is we have 2 Gaussians with the same variance that differ by at most 1 over n. And these distributions are going to be similar, and that's the property that I'm going to talk about in terms of the output being similar. So why am I using distributional stability? Why don't I just stop and say, hey, the empirical answer changes by at most 1 over n? And this is something that's sort of an idea that's cropped up in other parts of the literature, just looking at the stability of outputs in terms of how well they do.
Who's B?
There's like French names, STOC and Adaptivity. I'm sure I've mispronounced those. I mean, there are a couple of references. So it turns out that distributional stability is more robust than just looking at the stability of the value of the output. And essentially the way this works is because there could be a lot of information hidden in an output, in the low order bits effectively, even if the 2 values are very close. There's a lot of information there. Whereas distributional stability, because they're adding noise that is hidden. So it's a bound on the amount of information that's being released rather than just the bound on the value. And the other thing is that distributional stability works very well with adaptivity, and this is why we're able to get this square root k rather than linear and k dependence. Okay, so let me be a bit more precise about what I mean by distributional stability. So I'm going to say that the mechanism is stable if for any analyst, or any choices of queries that the analyst makes, and any sort of neighboring inputs, so by that I mean you just replace one of the sample points, the distribution on outputs in these two cases are similar. What I mean by the distribution on outputs, well, we have our sample here and our modified sample here. We feed that into this process, and then we get a transcript, which is a sequence of queries and answers. And in these two parallel universes, we get two different distributions. And I want these distributions to be similar. Now, what do I mean by distributions being similar? I need to quantify that. Now, there's actually a number of different choices you can make here. So you use the simplest thing is KL divergence. I don't know if you're familiar with that. You can also use Rényi divergence. But actually, what we've used in these papers is the similarity notion from differential privacy. That means that if you look at the event, the probability of an event under one distribution and the probability of that event under the other distribution, these probabilities are close to within a multiplicative factor and an additive factor. And this is the notion of similarity we're going to use between distributions. Okay, great. So I've defined what I mean by stability. Now I can tell you what stability buys us. So we have this generalization lemma. So it says that if your mechanism is stable in this differential privacy notion of similarity, and you look at a random sample, and you look at some output of M, so you can pick any one of the K queries that is produced, then the generalization error is small with high probability. Now, this lemma is actually a generalization of the usual Chernoff-Hoeffding bound. So in particular, our proof of this lemma does give an alternative proof of the Chernoff-Hoeffding bound with slightly worse constants. And the way you can see that is, imagine if you take a mechanism that doesn't look at its input at all and it just outputs a fixed query, then basically this bound here is exactly what you would get from the Chernoff-Hoeffding bound. It's not stated the way you usually see it, but this is basically equivalent. So this is a generalization of standard concentration inequalities that handles more complex procedures, and we require the stability requirement. Okay, so what does this lemma do for us? Well, the error that we want to bound, the population error, we just apply a triangle inequality. It's the empirical error plus the generalization error. Now, this means that if you have a mechanism that simultaneously produces answers that have low empirical error and is stable, and hence has low generalization error, then it's going to give you low error in the population. Now, the mechanism I showed you earlier where you add Gaussian noise, well, the empirical error is going to be the standard deviation of that noise, approximately. And it turns out if you do this calculation, the generalization error is going to be inversely proportional to the standard deviation. And so you choose the standard deviation to match these terms, and that's how you get the final result. So this is a very nice lemma, I think. So I've mentioned differential privacy. I'm sure some of you have heard of that. Cynthia, are you familiar with differential privacy? So I'm just going to put the definition up here again. So basically, it's a mechanism differentially private if changing one input means the output distribution doesn't change very much. Now, this definition was originally formulated for a completely different purpose, which is as a standard for privacy-preserving data analysis. And here we're referring to it as stability, and the definition and the intuition for why stability is a useful privacy criterion is that the stability criterion means that the details of an individual can't be inferred from the output of a mechanism. Now, differential privacy by now has a reasonably rich literature, and that means that we can actually just take results from differential privacy, combine them with this lemma that I showed you, and hey presto, we have mechanisms that are going to allow us to answer adaptive statistical queries, or even richer queries than statistical queries. So this one lemma allows you to, basically gives you dozens of mechanisms that you can apply for answering adaptive queries. Now, another perspective on this is that usually we think of privacy and utility being opposing forces. So, on one hand, we want to protect our data, but we want to access that data. And here, this result is showing us that these things can actually be working in unison in this setting. So the fact that you're doing privacy is actually allowing you to make sure your data looks like fresh data. It allows you to ensure that the results you're getting from your mechanism are generalizing to the whole population. Okay, great. Any questions at this stage before I move on to the lower bounds? Okay, great. So now I want to talk about the other side of things and look at the lower bounds. So why is it that we get this square root k dependence? Why is it that we need to do these sophisticated things? So I'm just going to put up the lower bound that we had earlier. And this is what I'm going to try to give you some idea of how this comes in. In particular, I want to give you some intuition for where the square root k comes from. All right, so I'd like to start by conducting a little thought experiment. We're going to change our model. We're going to just let the analyst peek at their data. And why shouldn't we let them? Why shouldn't we let the analyst look at their data? It's his data. Why should we keep it from him? Now, the problem with this is that now the analyst knows everything about the sample, which means the mechanism, he basically doesn't need the mechanism. And there's really no telling what he will do with that information. In particular, he would come up with a silly query like this. He could ask, are you in my sample? Now, if you conduct a phone survey and ask, do you own a phone, then you're going to get some biased results. That's basically what could happen in this setting. This is what was happening in the story I told you at the beginning of the machine learning contest. So obviously, if the analyst has unrestricted access to the data, the analyst knows the sample, then there's nothing we can do to prevent him from overfitting the data. And that's the lesson of this thought experiment. If the analyst learns the sample, then overfitting is possible. I mean, maybe the analyst won't do that, but we really can't guarantee anything. So in order to prove our impossibility result, we're going to basically show that the analyst can learn the sample anyway. Okay, great. So let's do another experiment. So I'm going to look at a simplified case where I'm going to assume exactly what the mechanism is doing. I'm going to assume the mechanism is outputting the empirical answers. Now this is a big assumption, but bear with me for now. And I'm going to assume that the analyst is going to ask uniformly random queries. So he picks a random function, random predicate, and asks that. Now this is exactly the story I showed you at the beginning with the machine learning contest. And we already know that this is going to result in overfitting, but I want to give you a different proof of that. And I'm going to assert that this proof does generalize to the general setting where we're not looking at empirical answers. Okay, so now let's look at this correlation quantity. So I want to look at the correlation between the answer that the mechanism gives and the value of the query on a fixed data point. Right, so the query is a random variable and the answer is a random variable depending on the query. Now it's a very straightforward calculation to see that we get this. So if x is not in the sample, then these two terms are independent. Right? Q of x does not contribute to the empirical answer. This term here is mean 0, so we're done. But if x is in the sample, then Q of x contributes about 1 over n to the answer. And so we get a correlation of about 1 over n. Okay, great. So this was just one query. I just had one query and one answer. What happens if we look at all of the queries? I'm going to sum up over query 1 through query k, and then look at this correlation. Now, if you're in the sample, then the expectation of each term is 1 over 4n. Sum that up, k over 4n, and you can easily calculate that the variance is about k over 60. And similarly, if x is not in the sample, then we get something with mean 0 and a similar variance. These things are approximately normal by the central limit theorem, but that's not too important, the exact distribution. Okay, great. So now we know we have some quantity that we can compute. The analyst can compute this quantity and this quantity. So now the analyst wants to know, given x, is it in the sample or not? And it turns out we can distinguish these, right? We can distinguish these two distributions as long as the difference in means is larger than the standard deviation. Right? So if these distributions are far enough apart, you can distinguish them, you can figure out what's in the sample and what's not. And then you just rearrange that and you get n being square root k. That's where the square root k comes from. Any questions at this stage? Okay, great. So the moral of this second story is that the sample is revealed by the correlation between the queries and the answers. So even though the analyst didn't get to see the sample, the analyst still figured it out. So we're back to the first story where the analyst is now able to overfit. Okay, so I made this massive assumption that the mechanism is outputting empirical answers. So we want to move on to the general case where we don't make this assumption. Right? Now we have to deal not with just a specific mechanism, but there's an infinite number of possible mechanisms. So we have to come up with a more general analysis. So the real key in the simple case was this equation here. It's just a simple analysis of correlation that really drove the whole thing. And this is the thing we need to generalize. Okay, so now in the general case, all we know is that the answer that's returned is close to the true answer on the population. Now, we can already see that it's not going to work out if we use uniformly random queries. And in the simple case, the analyst was able to do everything just by asking uniformly random queries. But if you ask a uniformly random query, then this quantity is always going to be, well, with high probability, this can be very close to 1/2 for interesting population distributions. Now that means that the mechanism could simply output 1/2 all the time. It would be accurate with high probability, but we'd get no correlation. There'd be no information. There's no way to re-identify the sample. So if you ask, basically if you ask stupid questions, you get stupid answers. If you ask uniformly random queries, you're going to get uninteresting answers. So you have to ask more interesting queries. And it turns out we can do this, and we can guarantee a weakening of this equation here. So what we can guarantee is that if you look not at the, so we're looking at the correlation again, but rather than looking at a fixed x, we have to sum over all possible x. And we get that this is larger than some constant. Right, so here if you sum over all the x's, you'll get 1/4. Here if you sum over all the x's, we'll get 1/12. So in a sense, we're saying that there's correlation on average. Rather than being able to say that there's correlation for each point in the sample, we're just saying that on average there's correlation. So it's a weakening of that side of the result. Now the distribution on queries is not that complicated. All I need to do is sample a bias uniformly at random. And then for each x, I'm just going to sample the value of the query. I mean, the query is itself a random variable independently with that expectation. It's very simple. It's a simple distribution, and it avoids this pathology that I mentioned, where you could always just output a constant. Okay, so that's sort of generalized half of this. Now we need to look at the other half. We need to make sure that if you're not in the sample, you get low correlation. Now this is a little bit more complicated, and you have to use some more tricks. But basically, we can use some reasonably simple tools from cryptography to hide the value of the query from the mechanism. Now, if the mechanism doesn't know the value of the query, it can't output an answer that's correlated with it. So, for those of you who are into cryptography, the way we do this is by interpreting the samples as cryptographic keys. And then if you don't sample a point, then you don't know the key, and you can't decrypt the query and access that information. Now, for those of you who are not into cryptography, basically we're just trying to rule out the silly case where the answer depends on something that hasn't been sampled, because that would be very unnatural. But we need to rule it out. Now you'll be wondering why the result I mentioned, the lower bound result, has this computational assumption. It assumes that it only works for efficient mechanisms or high-dimensional settings, and that comes from the use of cryptography. So because we're using cryptography, we're only going to get a little computational lower bound. However, if we're in the high-dimensional setting, then we can use information theoretic cryptography, which doesn't make any computational assumptions, and then we're going to get an unconditional result. So that's really all of the ingredients that go into the lower bound proof. Any questions? People seem puzzled by cryptography. So, I mean, I also want to mention that these lower bound results were also inspired by work in differential privacy. So, impossibility results in differential privacy led to these impossibility results for adaptive data analysis. So there's a two-way connection between the two. Okay, so looking at further work in this area, so there's obviously two sides. So we can improve the upper bounds. So that means coming up with better algorithms. Now, currently the best we can do is about square root k times a log k factor over alpha squared. That is a rather messy expression, and I think we should be able to get rid of that log k factor. But I haven't been able to figure out how to do it yet. But I think another direction to push in is to change the model and to come up with algorithms that work for less pessimistic settings. Right? Here if you look at our lower bound, we really assume that the adversary that the analyst was really trying to overfit the data. Now that's not necessarily a very realistic setting, so we might want to change the model to restrict the amount of adaptivity. Now there's been some work on this where you say, okay, there's a restricted number of rounds of adaptivity, and then we can get better results. But there may be other sort of other models that will allow you to make more interesting results. Another thing is that everything I stated here, the error was just a very simple additive alpha term. All I want is an error that's within an additive alpha. But this may not be the most natural way of measuring error, right? A lot of the times we're interested in multiplicative error, or we'd like the error to scale with the standard deviation of our data. That's what you would get in the non-adaptive setting. We have some partial progress on getting results that are not going to just be additive error, but will scale more like the standard deviation of the data. Okay, and then we can also work on trying to improve the lower bounds. So currently we have this square root curve at alpha, but my firm belief is that the right answer is square root curve alpha squared, which would match the upper bound modulo the log log. And we have some partial progress in that direction as well. Basically, we can show that for a large class of algorithms, which includes all proposed algorithms, this lower bound holds.
Can you say anything about that?
So basically, it's very similar proof. We're able to show that the negative of the generalization limit that I had. We're able to show that if you have less samples than this, then I can output a query that does have high generalization error. That doesn't necessarily mean that I have high population error, because the triangle inequality is not necessarily tight. So basically, any algorithm that is both empirically accurate and accurate on the population is subject to this lower bound. But you could have an algorithm that's accurate on the population but completely off on the sample it's given, which is very strange, very pathological, but we can't rule it out. And the other direction, of course, to push on the lower bounds is to come up with more natural queries. I mean, I saw a lot of people in the audience feeling a little perplexed when I started mentioning cryptography, because those are not natural statistical queries. And they are statistical queries, and they're efficiently computable, but in some sense, you could say these are probably not going to arise in practice. But I think we can probably make the lower bound look more natural. And I think we can hopefully sort of take the lower bound and use the same ideas and embed them into very natural queries. I would also sort of try setting it up so that the setting is not quite so adversarial. So we're not sort of thinking of an analyst who's really trying to shoot themselves in the foot, who's really trying to overfit the data. And the machine learning contest, I think, was an example where you have something that's sort of kind of a reasonable example of someone trying to overfit data. And it would be nice to have a sort of a similar story here rather than someone who's really just trying to prove the lower bound. Okay, so in summary, I've talked about this model of adaptive data analysis that comes from these earlier papers from 2 years ago. I really do like this model. And already we saw that empirical answers are not really going to cut it in the adaptive setting. But we have these other techniques which we know are essentially optimal for the adaptive setting, which yield an exponential separation. And on the upper bound, the key idea was that we have the stability criterion giving us generalization. There's a new way of proving generalization. And this builds a connection with information theory and differential privacy, which I think is a really neat idea that came out of this paper from Cynthia, Vitaly Feldman, Moritz Hart, Tony Patassi,
Reingold and Rothman.
Reingold and Rothman. Like always can't sort this. Okay. There's very, very nice ideas coming in there, and I think that's a really nice contribution from the differential privacy literature elsewhere. The lower bound is also building on ideas from differential privacy, and sort of the key idea, I think, is that overfitting is possible if you're able to figure out what the sample is. If there's enough information released through the queries to overfit, then we're really we're hosed in terms of proving generalization results. And really the underlying idea of this, of the proof, is that this correlation is enough to reveal that information. Okay. Any questions?
Thank you very much.
Well,
So yes, are there any questions? And if anyone's listening outside, please feel free to email me questions and I'll relay them to the speaker.
so we know that some of the attacks that show that by getting relatively accurate answers to enough linear queries, you can reconstruct the data set. We understand their role in this. This is how you learn the data set, and then your accuracy adversary just nails it.
Mm-hmm.
So presumably you could do the same thing with other kinds of queries that have been shown to teach too much about the database, like what did Kashyap Vishwanathan and Smith show? They were looking at logistic regressions or a few other kinds of regressions to do this.
Right.
I'm curious, you go through a lot of contortions going through the cryptography just to rule out trivial answers. Do you need the same sorts of things if you look at these other kinds of queries? Maybe trivial answers won't work anymore and you could skip the crypto.
I mean, in a sense, we know that the crypto is necessary
Yeah.
because we have these exponential time mechanisms that will otherwise circumvent them. I mean, I think really, if you want to avoid the crypto, which would be nice, you just have to make some sort of assumption, like, the mechanism doesn't look at the value of the query if on points it hasn't been given. All natural mechanisms will do this.
Yeah.
So it's kind of a reasonable
Just
assumption.
hard to define exactly what it means not to look at.
Right.
Okay.
So I've got a couple of general questions. I mean, I thought it was really nice. It seems really powerful, this sort of notion of adaptive data analysis you've got here, and your generalizability lemma, I thought was really nice way of helping me to learn about it. But so two general questions. One, in terms of the relation with differential privacy here, are there some differences here? So you went straight for this sort of Gaussian mechanism rather than, say, Laplace and so on. Is there some reason for that? And for example, if your x's were continuous rather than binary, which presumably would sort of cause some traditional problems in terms of stability for differential privacy, would it be similar here?
I use the Gaussian mechanism because people are more familiar with Gaussian noise than Laplace noise. You can use Laplace noise, it works just as well. In terms of discrete versus continuous, I don't think that matters too much. I mean, obviously, when I had this result about, the reason I said it was the reason I said that we were going to look at 0, 1 to the d, the specific d-bit data universe, is so that I had a convenient parameter for the low-dimensional result. And you could use different parameters. So you could say you have an arbitrary space. I'm going to look at the VC dimension of this space. So you use other. You could have a continuous space and still have some other motion dimension.
Just a different, sort of practical question. In terms of the kind of practical applications, the kind of adaptive data analysis that would be going on, I suppose I'm imagining, I work with social scientists who like having microdata sets that they do multiple analyses of and so on, and quite likely overfit in some ways. I'm trying to think how this kind of, the application of this sort of mechanism might help people who use microdata sets to do better analyses of those. But on the other hand, it seems to me that's not quite the kind of application you have in mind, because it's more of an aggregate sort of mechanism that you're dealing with.
So there were some really nice ideas in a later paper by the DFHPRA set of authors, where they sort of looked at, you don't put all of your data behind this differential privacy shield. You just sort of put your holdout set, so half your data behind this shield. And then you can have your half of your data that you can do whatever you want with. But when you want to go and at the end test your hypothesis, you'll use this separate holdout set, but you want to make it usable. And that's what these techniques would provide for you. So that's some sort of way of coming up with an intermediate between what people really would like to do, which is get their hands on the data, and having these strong guarantees. But in order to have these strong guarantees, you really have to tie your hands in terms of how you're able to access your data. Yes.
Could you assume like the data, if you split them, that is going to work, or what's the limitation of these techniques? Because it's real special social science element.
I mean, you are going to have to put some of your data behind this and keep some of the other data for this approach.
It's no different than all of the usual uses of a holdout set. It's just that you get to reuse it.
Right.
So if you're in a situation where the usual uses of holdout sets are valid, then this will still be valid.
Any other questions? I haven't received anything on email, so I think we're all okay there. Well, thank you very much. Thanks once again. Thank you.
Just the synthetic data, I guess, you sometimes think of synthetic data as
Yeah, well, we had this this workshop meeting having a big debate about synthetic data. Yeah, one of the test based just to test.
but in some sense there's some relation, isn't it? Instead of having synthetic data, you would have
Think about.
the application of this method.
Yeah. Yes.
Basic implementation.
Yeah, no, I mean, it depends what you want synthetic data for, and yeah.
Oh, thank you.
In that sense.
Do you have any feedback? I think it's same talk in 2 days.
Yeah, because things there. If you
Sure, you want to
Yeah,
use
I
this?
mean, it's synthetic data is there as a means to test.
Should we meet over there? Okay, that sounds good. Oh, thank you.
yeah. Yeah.
Good.
Yes.
Clearly done. Quite hard, some of the
Yeah, I mean, it's always a bit of a cultural response about these things.
But it's, yeah, I think statisticians are sort of, I guess you're starting to hear about this kind of thing. It's like people like Andrew Gallman and various people, I guess.
Right. I mean, it's like I said, there's this fully adversarial model. I think it'd be really interesting to try and sort of come up with an intermediate